So, good day everyone. We are here to find out or to tackle about solving rational zero theorem, also the Descartes rule of sign, and of course the upper and lower bound theorem. By the way, I'm Xavier Lance Di Mendoza from Tem Galileo, and we are here to solve problems involving these three theorems. So, the problem is, Lance is playing a bank heist in his video game Grand Theft Auto 5. In order to surpass the mission, he needs a PIN password to open the safe. Unfortunately, his partner can only hack a polynomial code. So the code is 6x cubed minus 5x squared minus 8x plus 3. How many are needed keepings? And of course, use the three theorems. So first, before we find out those pins needed to answer this problem, we should tackle first those three theorems. So the first one, so here is the picture of the bank case. So the first one is the Descartes rule of sign. Descartes rule of sign is used to determine the number of real zeros of a polynomial function. Again, only the number of real zeros, okay? So it tells us that the number of positive real zeros in a polynomial function f of x is the same or less than by an even numbers as the number of changes in the sign of the coefficients. The number of negative real zeros of the f of x is the same as the number of changes in sign of the coefficients of the numbers of f of negative x or less than this by an even number. So before we came to the steps, let us first look at this example. So the first one is, begin by determining the number of side changes. So the here in the example, f of x is equal to negative x raised to 4 minus 3x cubed plus 6x squared minus 4x minus 12. So as you can see, we were going to look at the number of changes. So in this part, from the first term to the second term, there are no change. Okay? So it is not counted. Again, we are looking for the number of sign changes here. And take a look at the second term to the third term. There is a change from negative to positive. And also to the third term to down to the fourth term, there is also a change of sign. Meaning there are two sign changes. So there are either 2 or 0 positive real roots. Next, we examine f of negative x to determine the number of negative real roots. So maybe you're wondering why there is 0 positive real roots. Again, there is a loophole here in the Descartes rule of sign, meaning it is the maximum, okay? Meaning the 2 is the maximum number of positive real roots, either 2 or 0. Okay, so later on we will discuss about that. So the same way in the f of negative x. So again, in changing the sign of f of negative x, we're just going to change the sign of those terms in an odd terms, meaning the cubic term, the linear term, and so on. Okay, so those are the one who will which will only be changed. Okay, so take a look at the new polynomial, negative x raised to 4 plus 3x cubed plus 6x squared plus 4x minus 12. So there will be only two changes, of course, the first term to the second term, and between the third term, the fourth term, and the constant. So meaning there are two sign changes. So there are either 2 or 0 negative real roots. So in the final step of it, there are 4 possibilities as we can see below. So positive real roots, again, we're going to find out all the possible combination, okay? So positive real zeros, 2, negative real zeros, 2, complex zeros, no. Since we're gonna find out if we're gonna find this if there we just subtract the total zeros to the positive or either the positive or negative real zeros in order to find these complex zeros, or also called as imaginary roots. Okay, so let's take a look at that on the second part of the table. 2 positive real roots and no negative real roots, meaning it is 0. So meaning we're gonna subtract 2 from 4 in order to find those imaginary roots. So 2 for the positive, 0 for negative, complex 2 or imaginary, and then the total zeros is 4. We just need to complete the number of total zeros, meaning the degree of the certain polynomial. So given this polynomial, we're going to find out the number of positive and negative, and of course the imaginary roots of a certain equation. Okay, f of x is equal to 6x cubed minus 5x squared minus 8x plus 3. Okay, so we need to find the number of changes of the certain equation. Okay, so let's put some curves here, and curves here. Okay, so 6x cubed, is there any other change between this and this? Of course, the positive and negative, meaning there is also change. And the second term to the third term, there is no change. Since negative to negative, no change. And of course, the third term down to the constant, there is also change in the sign of the given equation. So meaning, there will be 2 positive roots. But take note, since there is a loophole, we're just going to continue subtracting 2 until it reaches 1 or 0. Okay? So we're gonna minus 2 to the two positive roots, meaning the other root is 0. Okay? The same way, on the f of negative x, so how are we going to change this? Take a look at the odd terms. So since this is the in cubic, we're going to change this into 6x cubed, since this is a square term, meaning there will be no change. 5x squared, and linear term, of course, positive 8x plus 3. So again, take a look at the number of changes, okay? So this, meaning no change, this, change, and this, no change. Okay? So meaning, since there will be only one negative roots, no need for us to subtract 2 for that negative roots. So, let's tabulate it. Okay? Positive, negative, imaginary, total. Okay? Sorry. Okay? So, again, we have, the first one is positive, meaning we have 2. Okay? Let's first use the 2. And the negative is 1. Again, the total is 3. Okay? So, meaning, since there are 2 and 1, 2 plus 1, 3, no need for us to, or there will be no imaginary roots for this certain equation. So, 0. So, again, the positive real roots either 2 or 0. So, we're gonna use that 0. And then, 1 negative root. So, there will be 2 imaginary roots in order for us to get the total roots of 3. That's the Descartes rule of sign. Again, we're going to find out the maximum number of positive roots. As we can see in the key concepts here, the f of x gives the maximum number of positive roots, and f of negative x rather gives the greatest number of negative roots. And to find the imaginary roots, just subtract the total number of positive and negative roots from the highest degree, or the total number of roots. Descartes' rule of sign is a loophole and will only be used to find the possible number of real and imaginary roots. So that's the Descartes' rule of sign. So we'll be using this in order to find that number, or the total number of keys, meaning there will be 3 pins. Okay? So we're going to find those 3 pins. But beforehand, we need to understand this, the upper and lower bound theorem. So, upper bound theorem, it states that if you divide a polynomial using synthetic division, and this yields all non-negative numbers, then C is an upper bound to the real roots of the equation. So here, we're going to find out the boundaries of the roots, wherein it will give us clue wherein the number of roots, or the possible roots, we're going to find those combinations, or the given numbers. It will give us choices wherein it can be the roots of this equation, or it can be the zeros of this equation. So it is the upper bound. An upper bound is an integer greater than or equal to the greatest real zero. Okay, so note that 2 things must occur for C to be an upper bound. One is C is greater than 0, or positive, and the other is that all of the coefficients of the quotient as well as the remainder are positive. Lower bound, the same, or the other way around. The lower bound is an integer less than or equal to the least real 0. Okay. So yeah, take a look at the example. Show that all real roots of the equation x raised to 5 minus 5x cubed minus 10x squared plus 12x minus 20 is equal to 0. Okay, so C on C, let's apply synthetic division, negative 4. Just write the leading coefficient of each term. 1, 0, 5, negative 5, negative 10, 12, negative 20. And yeah, so as you can see, in the lower bound, as we notice, the second layer, should I say? The second layer is the 1, negative 4, 11, and negative 54, 228, and negative 932 shows, it is arranged randomly. I mean, positive, negative, meaning, it is arranged, what do you call this? It is arranged as positive, negative, meaning it is not all positive or all negative. And as you can see, note how C is equal to negative 4 is less than 0, and the successive signs in the bottom row of our synthetic division. Oh, that's the term, alternating. The bottom row of our synthetic division is alternating. Positive, negative, or negative, positive, the other way around, as long as it follows a certain pattern, which is alternating. It is considered as the lower bound. Okay? So, here, it gives an example of negative 4, meaning it's the lower bound for the real roots of this equation. Okay? So, let's apply the synthetic division. Upper bound, the other way around. But the only difference is that the bottom row of the synthetic division here are positive. So you know what that means? 4 is an upper bound for the real roots of this equation. Since negative 4 is a lower bound and 4 is an upper bound for the real roots of the equation. And that's the upper bound and lower bound theorem, stating only the boundaries of the possible position or the possible number or the possible real roots located. Okay, so let's try this on our pattern. Okay, so let's state that the boundary 3, let's synthesize this. 6, negative 5, negative 8, and 3. Let's see if it is the lower bound or the upper bound. Okay, so then, just, yan. 6 times 3, 18, 18 there's negative 5, 13, plus 3, 39, 31, and 63. No, 93. 96. Meaning, this is the upper bound. Because as you can see, the bottom row of the synthetic division are all positive. So, let's find out how about the negative 3? Okay. Negative 3 again. 6, negative 5, negative 8, 3. 6 times negative 3, negative 18, negative 23, negative 60, negative 69, positive 69, 61, times negative 3, we call it 61, 3, 1. So as you can see, this is the lower bound of the equation, since all of the bottom row is alternating from positive to negative. 1. Rational zeros theorem. So this is the moment of truth, because rational zeros theorem states if p of x is a polynomial with integer coefficient and if it's a zero of p of x is equal to 0, then p is a factor of the constant term of p of x and q is a factor of the leading coefficient of p of x. Okay, so in the rational zero theorem, we're going to find out all the rational zeros of a polynomial. So if we are going to compare it to the Descartes rule of sign, and they call this the upper and lower bound theorem, it is the one that will give us concrete answers of those rational zeros in a certain polynomial. So here are the steps. Let's apply it on our example. So the example is 2x raised to 4 plus x cubed minus 19x squared minus 9x plus 9. So here, all of the given or all of the needed questions, should I say, or all of the needed terms are given here. So the factor of constant term, factor of leading coefficient. So we're just going to look at the leading coefficient and list all its factors and the factors of the constant term. And then we're just going to set that as p over q. So as you can see, possible values p for those factors of constant 139, and of course the factors of leading coefficient, meaning 2, will be only 1 and 2, and this can be simplified to positive 1, so on and so forth. So as you can see in synthetic division, we're going to find, or we should say trial and error for those simplified roots. Okay, so any of this combination, we're going to try until we find until we get to the point that there will be no remainder. So as you can see here, negative 1, 2, 1, negative 19, negative 9, 9. Okay, so synthetic division, he gets 2, negative 1, negative 18, and 9. Meaning remainder is equal to 0, meaning it is a 0 of the polynomial, or it is the root of the polynomial. And the same way in the third 1/2, it is also the 0 of the polynomial. So for now, actually there's a shortcut in order for us to find the remaining zeros, the 2 remaining zeros, if you are down to the quadratic formula, quadratic equation. But here it is in 2x raised to 4, meaning we're going to find the another one in order for us to factor out, or you can simply factor the cubic if you can, but I recommend that when we are down to the quadratic function of the bottom row of the synthetic division, we can find those 2 remaining terms. So let's find out about this moment of truth. 6x cubed minus 5x squared minus 8x plus 3. So first, let's set this as p over q. Okay, so let's find out the number or those factors of this. So 3, meaning 1, positive, negative 1, and positive, negative 3. Okay? All over, factors of 6, we have positive, negative 1, positive, negative 2, positive, negative 3, and of course, positive, negative 6. So we're just going to simplify it, or we're just 1 over 1, or partner by partner, positive and negative, rather. Positive, negative 1/2, positive, negative 1/3, positive, negative 1/6, and the other way around, okay, positive, negative 3 over 1, positive, negative 3 over 2, positive, negative 3 over 3, and positive, negative 3 over 6. We're just going to simplify this. We'll just cross. How about this? Cross, positive, negative 1 over, or positive, negative 1. Okay? So, negative 1/2, here, positive, negative 1/2. And 1/3, no? Positive, negative 1/3. Positive, negative 1/6. Positive, negative 3. And positive, negative 3 over 2. Okay? So, here are the possible roots of the equation. Okay? Just going to erase this one. So, here are the possible roots of the equation. So, for us, we should use of course, the synthetic division. Let's try yung negative 1. Okay? Then this down, this 6, negative 5, negative 8, and positive 3. Okay? So, and 6, negative 6, negative 11, negative 3. Oh! Okay? We find the zeros of the equation. We're lucky. Because sometimes it is quite, not that difficult, but it's quite time-consuming if we didn't find the zeros out of this given combination. Okay? So, there's a shortcut here. No need for, actually, there's not a shortcut. This is the most applicable step. Okay? So, since we find we found out that negative 1 is the zero of this equation, we're just going to set this as quadratic equation, meaning 6x squared minus 11x minus 3. And we're going to factor this in order to find out those two remaining zeros. Okay? So, let's factor this out. So, we're going to use the quadratic formula, negative b positive negative square root of b squared minus 4ac all over 2a. Okay? So, substitute. Negative b, negative 11, positive negative square root of negative 11 squared minus, I think we should erase this one. Sorry, I only have this small whiteboard here. Again, negative 11x minus, plus. Okay, so negative 11, positive negative square root of b squared minus 4ac all over. Oh, what the heck? 4 negative 11 minus 4 times 6 times 3. Okay, all over 2 times 6. We're just going to simplify this one. And then negative 11 squared, we have negative, 100. Negative 121. 121 square root minus 4 times 6, 24 times 3, 72 over 12. The other is negative 11 minus square root of 121 and 72 over 12. So in order for us to find those two remaining, just simplify again. 121 minus 72. We got 49 over 72. Over 12 rather, over 12. Of course, square root meaning 7. Oh. 7. So we have negative negative 11 plus 7, okay, over 12. Okay, the other one is negative 11 minus 7 over 12. Okay, so negative 11 plus 7, okay, we have 4 over 12, 4 over 12, or 1/4. Negative 11 minus positive 7, we have 18 over 18 over 12 is equal to 3 over 2. So overall, we have, of course, the negative 1, and we have the pin. Okay, so we have, is right, negative 1, negative 1/3, and 1/3 rather, and of course the 3 over 2. So all in all, here is the pin needed for us to surpass the mission, and of course, perform successfully the bank case. So that's all for today. I hope you learned something new. That's all. Thank you.